Hello and welcome to my mystical emporium. My name is Bartholomew of the Mystical Order. Now, our journey begins many moons ago while I was traveling through antique lands in search of baubles and bangles and mystical items. In these lands, though, mystical items will only get you so far. The best thing to have is a friend by your side. And upon my journeys, I read many tomes of knowledge and wisdom. And there was one tome that had the greatest effect on me, where all good souls come to rest. Rodak's Hematology, Clinical Principles and Applications. Today I'll be explaining everything I've learned in hematology. Red blood cells are a specialized connective tissue that carries oxygen and nutrients to the tissues. Hematopoiesis, or making blood cells, occurs in the bone marrow. Hematopoiesis is the process of making blood cells. In terms of red blood cells, we have rubroblast, prorubrocyte, rubrocyte, metarubrocyte, reticulocyte, and erythrocyte. In terms of white blood cell hematopoiesis, we have two lineages, myeloid and lymphoid. The functional component of the red blood cell is called hemoglobin. Let's build a hemoglobin molecule. Now let's zoom into the mitochondria. Inside the mitochondria, we combine glycine and succinyl-CoA to make aminolevulinic acid. Now we leave the mitochondria and combine two aminolevulinic acids and avulanic acid dehydrogenase to make porphobilinogen. Now we combine porphobilinogen and uroporphrinogen, 3 catalase, to make uroporphrinogen. Now we combine uroporphrinogen with uroporphrinogen decarboxylase to make coproporphrinogen. Now we take this coproporphrinogen and we go back to the mitochondria and we combine it with coproporphrinogen decarboxylase to make protoporphrinogen 3. Now we take the protoporphrinogen 3 and combine it with protoporphrinogen 3 oxidase to make protoporphyrin. Protoporphyrin combined with ferroketolase makes a heme molecule. Now we take 4 heme molecules and combine them with 2 alpha globin chains and 2 beta globin chains, and that makes hemoglobin. There are about 270 to 300 million hemoglobin molecules in every single red blood cell in your body. Now let's get into our red blood cell indices. Our first indice is called just the red blood cell count, and that counts how many red blood cells there are per microliter. The hemoglobin is the oxygen carrying capacity. Hematocrit measures the amount of red blood cells in your total blood volume. Mean corpuscular volume is the average size of your blood cells. Mean corpuscular hemoglobin is the average amount of hemoglobin in each cell. Mean corpuscular hemoglobin concentration is the average amount of hemoglobin in each cell, which takes size into account. RDW is the distribution width, or how much each cell varies in size. Now we're going to get into cellular respiration of the red blood cell. This is the Embden-Meyerhof pathway. It makes 2 ATPs per glucose that is put into the system. The red blood cell needs ATP to retain its shape, integrity, and cation balance. This is the Rappaport-Lubering shunt. It produces 2,3-DPG. 2,3-DPG regulates hemoglobin's oxygen affinity. This is the hexose monophosphate shunt. It maintains the oxidative balance in the red blood cell and prevents oxidative damage. So that's how the red blood cell respirates. Now let's get into hemostasis. Hemostasis is the stoppage of bleeding. Let's go over each pathway. There's 3 pathways: the intrinsic, extrinsic, and common. In the intrinsic pathway, you have number 12, number 11, number 9, number 8, which leads us to number 10. In the extrinsic pathway, we have number 3, number 7, which leads us to number 10. In the common pathway, we start with number 10, and this is where the pathways converge. So we go from 10 to 5 to 2 to 1. And it's finally all stabilized by 13. Everything that I just explained about red blood cells can go wrong in some way or another. So here we're going to go into disease processes. This is anemia, not having enough red blood cells. This is polycythemia, or too many red blood cells. This is iron deficiency anemia, which causes the cells to be microcytic hypochromic, which means that they're small and they have too much central pallor. This is hemochromatosis, or too much iron in the blood, and also turn people's skin red. This is microcytosis, or cells that are too small. This is megaloblastic anemia. This can be caused by different vitamin deficiencies, and it causes the cells to be too large. This is spherocytosis. It's a congenital disorder that causes the red blood cells to lose their biconcave shape. So instead of being a disc with a depression in the middle, they're just a sphere. This is anisocytosis, or too much variation in the size between the red blood cells. This is reticulocytosis. This happens when red blood cells are released from the bone marrow, and you can notice a shift to the left. This may be a good thing if you're monitoring therapy for something like iron deficiency anemia. This is pyruvate kinase. If you remember, the Embden-Meyerhof pathway helps to maintain the red blood cell membrane. If we have a deficiency in pyruvate kinase, it breaks the Embden-Meyerhof pathway and it leads to echinocytes, or these types of cells. The most common type of deficiency in the hexose monophosphate pathway is G6PD deficiency. G6PD deficiency leads to oxidative damage in the cell, which causes a phenomenon known as Heinz bodies, or denatured hemoglobin in the cell. The spleen will sense these Heinz bodies and take a bite out of it, leading to bite cells, which look like this. It looks like there's a bite taken out of it. This is 2,3-DPG once again. A deficiency in 2,3-DPG leads to increased oxygen affinity to the cells and decreased oxygen delivery to the tissues. This is CDA, or congenital dyserythropoietic anemia. It represents stress on the bone marrow, causing 3 different types of anemias that you can acquire. Type 1, notice the internuclear chromatin bridges. Type 2, notice the bilobed nuclei. And type 3, notice the multinuclear red blood cell precursor. Now let's get into hemoglobinopathies. This is sickle cell. It's caused by a genetic mutation in the globin chain. This is hemoglobin C. This is hemoglobin SC, a combination of sickle cell and hemoglobin C. Now this is thalassemia. This is an inherited blood disorder that causes the body to produce insufficient hemoglobin. In the most severe forms, the patient is incompatible with life and dies quickly after birth or before birth. This is warm autoimmune hemolytic anemia. This represents the body's immune system attacking its own red blood cells. Tests we can do to determine if someone has an immune hemolytic anemia is a DAT. We would look at the indirect bilirubin and lactate dehydrogenase, or LD, which would be elevated. And we would look at haptoglobin, which would be decreased. One of the best tests to run on a hemolytic anemia is the DAT. The DAT determines whether the patient's red blood cells are sensitized by its own antibodies. This is cold paroxysmal hemoglobinuria. In the cold, it allows the body's own immune system to attack itself, so the patient must stay warm at all times. This is paroxysmal nocturnal hemoglobinuria. The acid-base imbalance at night causes the body's own complement system to lyse its own red blood cells, which causes the patient to wake up and pee blood. Now let's shift over to the white blood cell part of things. This is neutrophilia, or too many neutrophils. This is neutropenia, or not enough neutrophils. This is a leukemoid reaction. It's a non-malignant response to trauma. It causes a massive spike in white blood cells, but it is not cancerous. This is myeloperoxidase deficiency. It causes the neutrophil's ability to lyse cells intracellularly to be decreased. Now we're going to get into malignancies. Leukemia is a cancer of the bone marrow, causing uncontrolled proliferation of white blood cells. There are 2 ways to get cancer. The first way is through the activation of oncogenes. These are genes that cause cells to divide uncontrollably. The other way to get cancer is through the loss of tumor suppressor genes. It's essentially you're losing the brakes to stop cell proliferation, so your cells could divide uncontrollably. In acute leukemia, the cells are predominantly blasts or premature forms of white blood cells. Chronic leukemia is slowly progressing, predominantly comprised of mature cells. This is polycythemia vera, a slow-growing blood cancer where the bone marrow produces too many red blood cells. This causes thick blood, which comes with a high risk for blood clots. This is essential thrombocythemia, a rare chronic blood cancer where the bone marrow produces excessive platelets, increasing the risk of blood clots, strokes, and hemorrhage. This is chronic myeloid leukemia, a slow-growing blood cancer that is characterized by the Philadelphia chromosome, or the BCR-ABL gene. This is primary myelofibrosis, a rare chronic blood cancer where bone marrow is replaced by scar tissue. Now let's look at disorders of hemostasis. Hemophilia is a rare blood disorder caused by missing or low clotting factors, usually 8 or 9. This causes the blood to be unable to clot properly. This video is just scratching the very surface of what we covered this semester and last. This doesn't cover even close to the amount of diseases we covered, all of the tests we run, all of the techniques that we do. This didn't cover blood bank at all. I didn't include all the symptoms, all the tests, all the considerations that might come into diagnosing a disorder. This course really did make me apply myself and think really hard, and it made me a stronger student. I'm a stronger student now because I realized that I'm capable of anything. As long as I can read one letter, then I can read one word, then I can read one sentence, then I can read one paragraph, then I can read one page, then I can read one book. And if I can just read one letter, I can accomplish anything at all, and I can learn anything that I set my mind to. In the lab, I learned how to do all sorts of different tests to reveal different disease processes, and I believe this course did prepare me for clinical rotations. I will go into clinical rotations confidently due to the confidence that my instructors have bestowed upon me.